Hello, everyone. Welcome back to another Flan Talk. Today, we're very pleased to have Eshaan Nichani. He's a final year PhD at Princeton, advised by Jason Lee and Yushin Sun. He has done very interesting work in finding provable guarantees for the learning behavior of neural networks. And today, we're excited to hear about compositional functions. So, Ishan, thank you and take it away.
Great. Yeah. Thanks, Andy. And yeah, thanks to the organizers for having me today. Yeah, my name's Eshaan, and today I'll be presenting our recent paper, Learning Compositional Functions with Transformers from Easy to Hard Data. So this project is joint work with this amazing set of collaborators, Zishuan, Alberto, Alex, Daniel, Jason, and Denny. Okay, um, So the motivation for this work are the multi-step reasoning capabilities of current language models. So as many of you probably realize, LLMs are capable of solving complex tasks which require composing multiple intermediate reasoning steps. So one example are question answer tasks in natural language. These require a model to read a paragraph of a story. For example, the football game is in Los Angeles, the quarterback is John, and then answer questions about this paragraph, such as who is playing in the USA. Additionally, LLMs are used in domains such as coding or mathematics, where multiple steps of reasoning need to be composed in order to arrive at some correct answer. So these practical reasoning tasks often involve combining contextual knowledge, i.e. information provided in the prompt, with parametric knowledge, a term which has been used to refer to global facts that are not provided in context and must be learned via pre-training. So in this natural language example, the contextual knowledge is the associations football maps to, or Los Angeles maps to football, and quarterback maps to John. However, in order to complete this task, the model needs to be aware of the parametric knowledge that Los Angeles is a city in the US and that quarterback is a position in football. In coding or in mathematics, the contextual knowledge might be definitions or variable assignments that are provided in the prompt by the user. Whereas the parametric knowledge would be the information such as which theorem to use or which function to call. So the goal of our work is to understand how LLMs learn to perform such multi-step or compositional reasoning tasks. So in particular, we're interested in the following questions. What is a model for compositional reasoning, which includes both contextual and parametric knowledge? Okay. Secondly, how do transformers efficiently express such tasks? And finally, in my opinion, most importantly, how do transformers learn such reasoning tasks via gradient-based training? Okay, so our first contribution is that we introduce the k-fold composition task. We then prove that this can be expressed by a transformer with log k layers. Finally, we show that curriculum learning is both necessary and sufficient to learn the k-fold composition via gradient-based training. Okay. So now let me describe our k-fold composition task. And let's return back to our motivating example from natural language, here with some more information in the prompt. So here the prompt says the football game is in Los Angeles, the softball game is in Toronto, the quarterback is John, the pitcher is Sarah, who is playing in the USA. So one observation is that multi-step reasoning tasks can be viewed as function composition. So in this example, the input contains the description of two different functions. Sigma 1, which maps from the set of cities to the set of sports, and sigma 2, which maps from the set of positions to the set of names. The input additionally contains a query index x, here being USA. The parametric knowledge can also be described by a pair of hidden functions. Pi1, which maps countries to cities, and pi2, which maps positions to sports. So the target function that the model must learn is, given the input sigma 1, sigma 2, and x, to output the following interleaved composition, sigma 2 of pi 2 of sigma 1 of pi 1, evaluated at the index x. Okay. So in particular, the model must perform the following sequence of computations. First, it must map the index x, USA, to Los Angeles using the hidden permutation pi 1. Then it must compute sigma 1 of Los Angeles, in this case football. It must then compute pi 2 of football, in this case quarterback, and then finally compute sigma 2 of quarterback, which is John, and output the final answer of John. Okay. So in light of this example, let me formally define the k-fold composition task. We're going to make the simplifying assumption that all of the functions we consider are permutations, i.e. bijections, on the set of n elements. Okay. The parametric knowledge is going to be a tuple of k hidden permutations, pi 1 through pi k. So each of these are a permutation on the set of n elements. The target function, f sub pi, will be parametrized by this hidden pi. The input, or the contextual knowledge, is a tuple of k input permutations sigma 1 through sigma k, along with the starting index x in 1 through n. So the target function f sub pi is the function that maps any such tuple sigma comma x to the following interleaved composition of permutations. So this is just a generalization of the example on the previous slide to more permutations being composed and a larger vocabulary size. Okay, so let me make a few remarks about this definition. I'd first like to emphasize that the inputs to the target function f sub pi are the contextual permutation sigma and the index x. Okay, so in particular, sigma and x can vary from example to example, while the pi remain fixed. Okay, so in addition to this following example prompt that I gave, another input could be the following prompt, something like the football game is in Toronto, the soccer game is in Paris, and so on. So here the input sigma and the query index x differ. However, the parametric knowledge required to compute the answer remains the same. Moreover, we note that the target function f sub pi is parametrized by the hidden permutations pi. Okay, so considering all different values of pi, the hidden pi thus give us a function class script f. So as we will see later, we can really consider the learning problem of learning this function f sub pi, or equivalently learning the hidden pi, from samples that look of the form prompt 1 or prompt 2. So to summarize, here is a diagram of the task. The red arrows are the hidden permutations, and which are not provided in the input, whereas the green arrows are the input permutations, which are provided in context. So a couple minor notes. We're going to encode each permutation using n tokens, one for each element of the domain. And as such, the total sequence length that gets passed into the model is of length k times n. Okay. Finally, we remark that this k-fold composition is related to other compositional tasks, such as the automata simulation or k-hop induction head, whose expressivity has been studied in prior works. Okay. So before I move on, I guess I'll pause here. Are there any questions about the definition of the k-fold composition task? Okay, great. So let me continue. So our learner for this task will be a multi-layer transformer. So I guess this is a neural network seminar, so people are probably familiar, but let me briefly go through the definition of the transformer. So the key building block is a self-attention head. So this is going to take as input a length t sequence of d-dimensional embeddings and output another length t sequence also of d-dimensional embeddings. So the self-attention head will be parametrized by d by d key query and output value matrices WKQ and WOV. Here we don't really distinguish between parametrizing the K and Q individually versus just parametrizing their product because expressivity-wise, these are the same. Okay, so in the self-attention head, each output is going to be a convex combination of the values WOV times XJ, where the weights in this convex combination, i.e. how much token I attends to all other tokens, will be given by the following softmax function. And we can succinctly write the formula for self-attention as the following, where the softmax function is being applied to the matrix column-wise. So a multi-layer transformer simply composes multiple of these self-attention heads in series. So we start off with our input, which is just a sequence of T tokens. We have some embedding layer phi, which maps token comma position to vectors in RD. These initial embeddings are then passed into the first self-attention layer. And the output of this self-attention layer is then added back to the original embeddings, i.e. through a residual connection, giving us the following formula for the first layer embeddings. This process is then repeated for L layers, where again, the output of self-attention keeps getting added back to the previous embeddings, until finally we have some readout layer psi, which maps the final layer embeddings to an n-dimensional output at each position. So one perspective that's useful to keep in mind when thinking about how information propagates to the transformer is that of the residual stream. So here we consider each token having a residual stream, which is its embedding at all layers. And this residual stream acts as some sort of memory or communication channel. Okay, how to think of this is, at the input to the first layer, we have some d-dimensional embedding for each position, and each self-attention layer performs its attention computation by reading some information from a certain subspace of that residual stream, and then uses its value matrix to output the output of self-attention to some different subspace of this stream. And so as we go through the construction, we're going to use this viewpoint of attention heads reading from and writing to the residual stream to think about how information is propagating layer to layer. Okay. So our first question, so now that we've introduced the k-fold composition task and our learner of a multi-layer transformer, our first question is to understand whether there exists transformers which can efficiently express the k-fold composition task. It turns out that the answer here is yes, and that this can be done via parallelism. So a number of prior works have shown that transformers can efficiently perform computations which are efficiently parallelizable. Okay, so some examples in the literature include the k-hop induction head, simulating a finite state automata, or simulating problems that can be solved by shallow circuits. And in all of these cases, these are problems which can be easily parallelized. And the general theme is that depth being equal to log of the sequence length suffices for expressivity. So we, in the k-fold composition task, the construction proceeds very similarly. And formally, we show the following. So let's assume that k is a power of 2. Then there exists an embedding function phi with embedding dimension k times n, such that for any choice of the hidden of the parametric knowledge pi, there exists a log k plus 1 depth transformer which exactly expresses the k-fold composition f sub pi. Let me go through the high-level idea of the construction first, and then walk through more details in the following slides. So the high-level idea is just to build a binary tree. So we're given as input the permutations sigma 1 through sigma k. The first attention layer is going to compute the compositions sigma I of pi I for each I. And this is done by encoding the hidden pi in the first layer key query matrices. The second layer is then going to compose the adjacent compositions sigma I plus 1 and pi I plus 1 with sigma I and pi I to obtain the following new permutation, which we call hop 2. This is just composing two sets of permutations starting from the index I. The output of the second layer will then be these hop 2 permutations. Layer 3 can then compose two adjacent hop 2 permutations to create a hop 4 permutation. And this process continues with the fourth layer composing two adjacent hop 4 permutations to get a hop 8 permutation, and so on, until after log k plus 1 layers, we have computed the k-fold composition. So now let me walk through each of these individual steps in slightly more detail. Okay, so Okay, now let's consider this expanded example with multiple sentences. So this corresponds to k being equal to 2. There are 2 input permutations, and n being 3. There are 3 vocabulary elements for each permutation. Okay. So in the context, we see that there are 2 contextual permutations, one mapping cities to sports, and one mapping positions to names. And so recall in the formal definition of the k-fold composition, each input was a permutation operating on the set of n elements. Okay, so in order to map this example to a something of that form, we're just going to pick an arbitrary labeling of the different vocabulary elements in each permutation. So we're going to, for example, let Los Angeles correspond to 1, Toronto correspond to 2, and Paris correspond to 3. Okay. And then similarly, for the input space, in this case being a country, we're going to pick some arbitrary ordering of possible countries as well. So the input to the transformer is going to be a length t sequence where each permutation is represented by n elements. So the input would be consist of 6 tokens of the following form. Okay. So first, the embedding is going to do the following. So in order to embed the token element sigma I of j, where here I is the index of the permutation and j is the element between 1 and n that's being permuted, we're going to encode this element as follows. First, we're going to have a one-hot positional encoding for the element I comma j. And this is some in k times n dimensions. The next k times n dimensions will be a one-hot positional encoding of I, and the output of the output of the permutation sigma I of j. This is also going to be in kn dimensions. And then finally, the rest of the embedding is padded with zeros. And this will be used for the computation in later layers. So we can associate with each tuple I comma j, the original word in the example. So for ease of explanation, we can think of the input, we can think of the embedding being of the following form. So for the map Los Angeles goes to football, we can think of a one-hot embedding of the words Los Angeles in the first kn dimensions, and then football in the next kn dimensions, and so on. Okay. So this will be the output of the embedding layer. And crucially, this does not depend at all on the hidden information pi. Okay, so now let's see what happens in the first layer of the transformer. So the first layer stores the parametric knowledge pi I and computes sigma I of pi I for each I. Okay. So how is this done? Let's remember let's look at what happens for pi 1. And let's remember that pi 1 is just some permutation that maps 1 through 3 to 1 through 3, or equivalently some function mapping countries to cities. So first, the first layer key query matrix, WKQ, is going to make the I comma j token attend to the I comma pi I of j token for all values of I and j. So let's look at what happens for I and j being equal to 1. We know that pi 1 of 1 is 2. Canada maps to Toronto, we see on the right. And as such, we want the 1, 1 token to attend to the 1, 2 token. And this can be done because we have one-hot embeddings, picking the correct index of the key query, or the correct entry of the key query matrix to be sufficiently large, and all the other indices to be 0. And specifically, the key query matrix will be a block diagonal matrix, which encodes each of these hidden permutations pi I. Next, we note that this I comma pi I of j token is going to contain I sigma I pi I of j in its residual stream, based on our choice of embedding. Okay, so here pi I of j was Toronto, and sigma 1 of Toronto was softball. So this token contains softball in its residual stream. And as such, the output of self-attention can then use the output value matrix to copy this specific block, softball, into the residual stream of the original token, specifically in the dimensions which were zero. Okay, so we're using these zero dimensions as some storage, and the embedding corresponding to softball gets copied into this storage. Okay, so this can then be done for every index I comma j in the sequence, such that the output of the first layer attention looks like this. Okay. So the output of the first layer, the embeddings of the first layer will encode the following. So let's look at the residual stream corresponding to the tokens in sigma 1. These will encode sigma 1 pi 1 of j for all the different j. So recall that we picked some ordering of the countries. You let Canada correspond to 1, France correspond to 2, US correspond to 3. And in this case, the quantity that's in the residual stream here corresponds to the sport that's being played in that country. So softball is being played in Canada, soccer is played in France, and football in USA. And so we see that indeed we have computed sigma 1 pi 1 of j for all the different j. The same thing is done in the residual stream of the next 3 tokens, but in this case, sigma 2 of pi 2. And here it's the person or the name corresponding to each sport based on the numbering we picked for each sport. Okay, so I think this was a lot of details in a row, so maybe I'll pause here. Are there any questions about how either the embedding works or how the first layer construction proceeds?
Just confirmation. So in the residual stream, we'll store the intermediate value after the first layer, and that'll be preserved over all the other layers as well.
Yeah. So that's this information, I guess, as I'll show in the later layers. This information gets preserved as you propagate through later layers. And this is because we've just chosen the embedding dimension to be sufficiently large. So the depth L is log K. And so the embedding dimension is Kn times log K. So there is like a specific block corresponding to the output of each layer, such that when you pass it into the next self-attention layer, the output then gets rewritten to a new block of all zeros and doesn't overwrite any information that was that had previously been written. Great. Yeah, thanks for the question. Great, yeah, so this is the output of the first layer. So now let's walk through, okay, what happens in the second layer. So the second layer is going to compose adjacent sigma I and pi I permutations in order to compute some hop2 function. How this is done is that the second layer key query matrix is going to make the I comma j token attend to the I plus 1 sigma I pi I of j token for each I and j. Okay, so let's look at what happens to I and j being 1. We saw that sigma 1 of pi 1 of 1 was just softball, i.e. 1. And so the very first token is going to attend to the 2 comma 1 token, in this case, the token containing goalie. So this token contains the hop2 function in its residual stream. Since we've already computed sigma I plus 1 pi I plus 1 of this token in the previous step, in this case being Sarah, this is simply the hop2 function of the original first token. And as such, we can then use the value matrix to copy this embedding back into the residual stream of the original token to compute the hop2 function. So then this process proceeds for every token in the sequence, such that the output of the second layer attention looks something like this. And in particular, the residual stream of the first 3 tokens contains the hop2 function of the numbering of our indices. So hop2 of 1 or Canada is Sarah, hop2 of 2 or France is Charlie, and hop2 of 3 or football is top 3 of USA is John. So the residual stream encodes these hop2 functions. And so now, in order to compute the output, one simply needs to read out the answer from the token corresponding to the input index we care about. In this case, it's France. So one simply needs to read out the answer from this specific block of the residual stream, which can be done using the readout layer psi to produce the desired answer, Charlie. Okay, so this just described what happened in the first layer and the second layer, but the rest of the construction proceeds, analogously to the second layer. So as like a brief overview, let's say that, let's assume that layer L has computed the hop 2 to the L minus 1 function. So it's composed 2 to the L minus 1 consecutive permutations. The Lth layer key query matrix will make the I comma j token attend to the very specific I plus 2 to the L minus 1 and hop 2 to the L minus 1 of j token. The reason that attending to this token is useful is that it contains this very specific hop 2 to the L minus 1 function evaluated at I plus 2 to the L minus 1. And as such, this is just exactly equal to hop 2 to the L of the original token. This can be then copied into the residual stream. So the L plus 1th layer is simply computing hop 2 to the L. Okay, so I think the details of how this specifically happens are a little bit, they're a little bit detailed, but I think, the high level takeaway is that we can double the number of permutations that are being composed through each layer. And so overall, after log k plus 1 layers, it's possible to compute the hop k, i.e. the original k-fold function. Okay. So this concludes the result for expressivity. And so are there any questions about how the k-fold composition is expressed by the transformer? Okay, awesome. So we've shown that this function f sub pi can be efficiently expressed by a transformer with log k plus 1 layers. The next question, however, is whether f sub pi can be efficiently learned from samples via gradient descent. Okay, so we're specifically going to consider learning with respect to the uniform distribution over the input space X. So this means we sample all the permutations uniformly at random, as well as the index X. It turns out that the answer is no. And formally, we prove a statistical query, or SQ lower bound, showing that it is computationally hard to learn the function class F. Okay, so in the SQ model, the learner gets to interact with the target function f sub pi as follows. The learner gets to specify any query Q, which maps input-output pairs to some real number, along with the tolerance level tau. For each query that the learner makes, the SQ oracle will return a noisy estimate Q hat, which is within tau of this population average of Q. So many common algorithms, such as gradient descent, can be understood in this SQ model. So indeed, if you write down the gradient with respect to some parameter, the population gradient can be simply expressed as some population average of a specific query Q. Okay, so as a result, the number of queries that are needed to learn in the SQ model is a useful proxy for the computational difficulty of learning via gradient descent. Okay, so our main result is the following. We show that any SQ learner for this function class script f, so varying over all possible values of the hidden permutation pi, must either make the number of queries exponential in k, or use tolerance exponentially small in k. So one common heuristic is, say our algorithm is mini batch SGD with n samples in each batch. So the mini batch gradient is going to concentrate to the population gradient at a 1 over square root n rate. Okay? As such, we can think of the mini batch gradient as simply a noisy estimate of the population where tau is 1 over square root n. And so a common heuristic is to just associate tau with being 1 over square root number of samples. And using this tells us that SGD either requires exponentially many queries or exponentially many samples in order to solve the task. Let me provide a high-level proof idea. So the goal is to construct an exponentially large subset of the function class script f, which is nearly orthogonal. So let's recall that this function class script f consists of the k-fold functions f sub pi, as we let pi vary through all possible tuples of permutations. So for two different tuples of permutations, pi and rho, the inner product that ends up being relevant is the following quantity, which is essentially some measure of how correlated the two functions f sub pi are over the randomness of sigma and x. Okay. So the first thing that we can show is that this inner product just depends on the number of overlaps between the permutations pi I and rho I for each I. Then, given this explicit formula for the inner product, it suffices to construct a subset of script f, which is very large, in this case, grows like n to the k, such that the inner product between any two functions in this subset is exponentially small. Okay. So from this formula, I think you can kind of guess how this could be done. I guess if you're going to pick arbitrary pi and arbitrary rho, they probably agree on a constant number of elements in each permutation. And as such, their inner product is going to be, this product of some constant divided by n to the kth power. And so their inner product will be something that's exponentially small in k. And so the construction it's not exactly just choosing enough random functions, but if you do choose two random functions, their inner product is going to be very small. And that allows us to choose this very large set such that this is true. And once this very large set is established, the SQ lower bound follows from standard arguments in the SQ literature, which essentially say that if you have a large set of functions that are nearly orthogonal, you need to make a lot of queries in order to rule out each one by one. So this concludes the lower bound against learning via SGD. Are there any questions about the SQ model or the high-level proof idea here? Okay, great. So we've now shown that, transformers can express this task, but learning via SGD is hard. So what can we do to get around this? Well, in our lower bound, we showed that learning from samples of the k-fold composition alone, i.e. only seeing sigma and then the output of the entire composition, learning the pi from this is difficult. However, training on easier examples of k prime fold data for k prime less than k, commonly known as curriculum learning, can indeed lead to efficient learning. So the parallel construction we talked about motivates a natural easy to hard curriculum. Okay. So let's recall that we've defined these hop R functions, permutations, to be the composition of R consecutive permutations in the input. We thus consider the following easy to hard curriculum learning algorithm. We're going to initialize all of the output value matrices to just be their ground truth, and only consider training the key query matrices via gradient descent. In each Lth stage, we're going to consider the cross entropy loss of predicting the hop 2 to the L minus 1 function using the output of the Lth layer. And we're going to take a single gradient step on all of the key query matrices for predicting this label. Our main result is that this curriculum learning algorithm indeed is able to learn the k-fold composition with a sample size that is polynomial in n and k. All right, so in particular, while naively training on the k-fold composition alone requires exponentially many samples, curriculum learning can succeed with polynomially many samples. Altogether, this demonstrates that easy examples or intermediate supervision is essential for transformers to be able to learn complex tasks via gradient descent. Okay, there's a question. What do you mean by initialize all the output value to the ground truth? Yeah, so this is a good question. So in the construction, we saw that the output value matrices performed the role of routing information from the correct subspace of the residual stream to the other correct subspace of the residual stream. And specifically, the construction is the output value matrices end up being these block matrices, which are identity in one specific block and zero everywhere else. And so in our main theorem, we don't focus on training these matrices at all. We actually fix them to what they should be in the construction. And we only look at training the key query matrices. I think one reason why I think this is okay is that, these output value matrices only perform the role of routing, and they don't store any information about the hidden pi themselves or what tokens each token should attend to. And I think this also just allows it to be easier to understand the dynamics. Okay. So in practice, it can also be challenging to design an explicit curriculum. And language models are often trained on just some large data set containing a mixture of lots of different examples of different difficulties. So instead, we can also extend our previous theorem to this mixed training setting. And so in particular, if one were to train on a data set, which is a mixture of 2 to the L minus 1 hop data, where L ranges between all values between 1 and the depth capital L. Here we show that gradient descent can also learn the capable composition in polynomial sample complexity. And so here, rather than using a different loss for each gradient step, we just consider the overall loss, which is a sum of the losses of 2 to the L minus 1 hop data for each value of little l. And I think this can be thought of some type of maybe multi-token prediction. You're trying to simultaneously predict multiple hops or multiple difficulties of examples all at the same time. Okay, so let me give a high-level proof idea. So in the curriculum learning setting, in the out stage, i.e. this is predicting the hop to the L minus 1 function, it turns out that just the gradient of the key query matrix at zero initialization ends up just being proportional to the ground truth. So it does exactly the operation of causing each token ij to attend to the correct other token in the construction that I described. We do have to deal with the other layers in the network. And so the layers L prime, which are less than L, the gradient to these layers ends up being small due to the saturation of softmax. So layers 1 through L minus 1 are the attention patterns here are roughly some hard max attention pattern where each token is attending to some fixed other token. And as such, the softmax is saturated, and so the gradient is small. On the other hand, the layers L prime greater than L receive no signal because we're simply using the output of layer L to predict the hop to the L minus 1 function. As such, the only key query matrix that has non-trivial update is this Lth layer. And assuming that layers 1 through L minus 1 compute the correct thing, the gradient at zero initialization is proportional to the ground truth. And so one gradient step allows WKQL to grow from 0 to the ground truth. And as such, after the Lth stage, the model can correctly predict the hop 2 to the L minus 1 function. In the data mixture setting, it proceeds similarly, but the challenge is now that there is signal coming from all the hop 2 to the L minus 1 functions simultaneously. So if the layer L is not learned, i.e. it's close to 0, no signal gets propagated to the later layers because the effect of layer L being 0 is to just average the information that's being passed into that layer. And as such, there is no signal to any of the later layers. So layer L cannot learn until layer L minus 1 learns. And so what ends up happening is that, okay, in the first step of GD, layers 2 through capital L cannot be updated and layer 1 gets updated. Then once layer 1 gets updated, in the second step of GD, there is now signal that is being passed to the second layer, and it grows to its ground truth, and so on. So in this data mixture setting, although all the examples are being presented at the same time, this actually implicitly induces some sort of curriculum learning where only the Lth layer gets updated in the Lth stage, and each of the intermediate hop 2 to the L minus 1 functions are learned sequentially one at a time. Um, I think the specifics of why the gradient end up being proportional to the ground truth are a bit more complicated, and we have some proof sketches of this in our paper if you're interested. So in order to here are some simulations which support the main theoretical results. So the top two plots follow exactly the theoretical setting of the curriculum learning and mixed training algorithms, where we use the same embedding, we fix the value matrices, and we just train the key query matrices via gradient descent. So in the curriculum learning setting, we see that each token or each consecutive hop gets learned in the correct step, such that after enough steps of GD, all the hop functions are learned. And the same ends up being true in the mixed training setting as well, where this jump after all the hops are learned corresponds to having to take a gradient step on the readout layers. The bottommost plot is a slightly more realistic setting where we have a standard encoder-only transformer where the input is not these one-hot embeddings, but just rather the labels of the permutations. And we use, learnable embeddings, MLP layers, layer norm, etc. And here we indeed observe that training on the fourfold data fails to learn, while mixed training, in this case, a mixture of 1, 2, and 4-fold data, succeeds after not too long. Okay, so let me make a couple remarks. So one interesting thing is that this k-fold composition exhibits a statistical computational gap. So the information theoretic sample complexity to recover the hidden pi is just log cardinality of the function class, in this case, kn log n. However, a computationally efficient SQLearner requires n to the omega k samples to learn. So this is reminiscent of the k-sparse parity problem in d dimensions. Okay, so this is like you're given a Boolean vector and you need to output the parity of k hidden bits. This information theoretically only requires k log d samples, but there are SQ lower bounds that say that actually d to the k samples or compute are required to learn this efficiently. One distinction between our compositional function and the k-sparse parity is that k parity is actually expressible by either a one-layer transformer or a two-layer neural network. However, the k-fold composition fundamentally requires larger depth and is thus fundamentally a compositional task which requires multiple intermediate steps. I want to make one other remark about the embedding dimension. So as some of you may have noted, other parallel constructions in the literature require an embedding dimension that only scales, say, like logarithmically with the input length, whereas we require d to be k times n. Okay, so one reason for this is that we are trying to use a fixed embedding that is used that can express the task for any choice of the hidden information pi. And so since log of the size of the function class is k times n, in order to just via a parameter counting heuristic, in order to express f sub pi for all possible values of pi, there need to be at least k times n parameters in the network. Okay, so this is just something that we need to because we fixed the embeddings. On the other hand, if we allow for trainable embeddings, then a construction with a much smaller embedding dimension exists. And this can be simply done by the embedding function storing these hidden permutations pi. However, this is, I think it's unclear whether specifically choosing this embedding function to store the information is realistic. And it's also challenging to show the learning dynamics of the specific embedding via gradient descent. So yeah, this is just one particular note. Yeah, so to conclude, the high-level takeaway that I'd like to make is that while expressivity has been fairly well studied in the transformer theory literature, it's not necessarily true that tasks expressible by a transformer are learnable via gradient descent. And this question of learnability is something that's more subtle in that it depends a lot on the underlying data distribution. So we showed that it's computationally hard to learn this k-fold composition directly Yet it's easy to learn via modifications to the training setup, such as using curriculum learning, mixed training. And it's been observed in other works in practice that other forms of intermediate supervision, say things like multi-token prediction or changing the proportion of the weights of examples in the data distribution, this can also lead a problem to go from being computationally hard to learn to learnable. And so I think one really interesting future direction is to kind of try to go beyond these expressivity guarantees to prove either upper bounds for learning different sorts of algorithmic tasks via gradient descent, or figure out a way to characterize the complexity of learning via gradient descent for kind of more general algorithmic tasks. And moreover, what are other ways beyond just this curriculum or intermediate supervision where one can either change the data distribution, the algorithm, or the loss to affect the complexity of learning via gradient descent? And I think this could be very interesting to the transformer theory or deep learning theory community more broadly to think about how to go beyond tasks such as, say, parity to really fundamental compositional or algorithmic tasks which look closer to the modern language modeling setting. So yeah, thank you very much for listening. Here's the link to our paper, and I'm happy to answer any questions that